So today's lesson is over simplifying cube and other roots. We've mainly dealt with square roots up to this point, but now we're going to talk about simplifying roots that are bigger than square roots. So just like with square roots, whenever we were finding our square roots, we wanted to find the biggest perfect square that goes into our radicand, the number under the radical. So for for square roots, cube roots, we want to find the biggest perfect cube that goes into the radicand, or the number under the radical. So you may want to have a list of your perfect cubes, and we get our perfect cubes the same way we got our perfect squares. We are just cubing each number. So 2 cubed is 8. So 8 is a perfect cube because if I take the cube root of it, I get 2. 3 cubed gives me 27. That's 3 times 3 times 3. 27 is a perfect cube. If I take the cube root of it, I get 3. The next one, 4 cubed, gives me 64. 64 is a perfect cube. If I take the cube root of it, I get 4. 5 cubed is 125. So 125 is a perfect cube. 6 cubed gives me 216. So 216 is a perfect cube. Take a cube root, I get 6. And we could do that for all of our numbers. So all the circled numbers here are our perfect cubes. So when we're taking the cube root, we want to find the biggest perfect cube that'll go into our number under our radical. So let's look at some examples. For our first one, we have the cube root of negative 128. So we want to find our biggest perfect cube that goes into 128. Now if you notice here, there's a negative number under our radical. If I gave you the square root of a negative number, I'm not able to do that. I don't have any real roots if I square root a negative number. Because remember, square roots, we're asking ourselves what number times itself gives me this number under the radical. There is no number in existence in our real numbers that will give us a negative number if you multiply it by itself. Because if you multiply a positive by itself, you're multiplying a positive times a positive, which will give us a positive. If you multiply a negative times itself, you're doing a negative times a negative, which is also a positive. So that if I take the square root of a negative number in Algebra 1, there's no real roots. You'll learn about that in Algebra 2, how you can take the square root of a negative number. But for now, for Algebra 1's sake, we cannot take the square root of a negative number. We can, however, take the square root or the cube root of a negative number, because we're multiplying a number by itself twice. So, once again, we want to find the biggest perfect cube that goes into negative 128. Our biggest perfect cube that does that is 64, so we're going to do negative 64. Negative 64 times 2 gives me negative 128. Now, the product property for square roots also applies to cube roots. So I can break negative 64 into its own cube root and 2 into its own cube root. Now the cube root of negative 64 would be negative 4. That'd be negative 4 times negative 4 times negative 4, which would give me negative 64. And then I am not able to take the cube root of 2, and there's no perfect cubes that go into 2. So this is my answer right here, negative 4 cube root of 2. So we found our biggest perfect cube, took the cube root of it, and that's us simplifying our radical. So let's look at letter B. We have the cube root of 125, x to the 7th. Now 125 is a cube root itself. So I don't have to break 125 down into anything. I can just keep it as 125. Now I need to break x to the 7th down into something that I can take the cube root of. I want to break it down to have an exponent that is a multiple of 3, because then I would be able to take the cube root of it. So the next biggest, or the multiple right under 7 of 3 would be 6. So I could break it down into x to the 6th times x. Now the cube root of 125 will give me 5, so I can take that out of the radical. Cube root of x to the 6th would be x squared. I just took my 6, divided it by my index. That gave me my new exponent for x on the outside of the radical. I cannot take the cube root of x, so it just stays under the radical, and here is my simplified expression. So once again, you're just finding the biggest perfect cube that goes into your number under the radical, the radicand, and you take the cube root of it, and then that is us simplifying our cube roots. Letter C. We have the cube root of y over 216. Just like the product property still applies to cube roots, the quotient property also applies. So I can give my numerator its own cube root and my denominator its own cube root. That's our quotient property. Now I'm just going to simplify each cube root. I cannot take the cube root of y, so it just stays as the cube root of y. And then the cube root of 216 gives me 6. This fraction right here cannot be simplified any further, so this is my answer. So let's just go look at some more examples. Sorry, the numbering's out of order. These are just from the book. So number 9, we have the cube root of 54. So once again, I want to find the biggest cube root, or perfect cube, that goes into 54. That biggest perfect cube is 27. 27 times 2 gives me 54. Taking the cube root of 27, I get 3. I cannot take the cube root of 2, so it stays under the radical. There's my answer for number 9. Number 10, cube root of 16, x to the 4th. My biggest perfect cube that goes into 16 would be 8 in this case. And then 8 times 2 gives me 16. And then I also need to break x to the 4th down into something I can take the cube root of. So remember, I want an exponent that is a multiple of 3. So I can break x to the 4th down into x to the 3rd times x, because 3 is a multiple of 3. So now let's take the cube root of the things that we can take the cube root of. I can take the cube root of 8. I get 2. 2 times 2 times 2 gives me 8. I cannot take the cube root of 2, so that will stay in the radical. Taking the cube root of x to the 3rd, I'm dividing the exponent by the index. So 3 divided by 3 gives me 1. So that'd be x to the 1st power, or just x. And then I cannot take the cube root of x, so that'll also stay under the radical. So I've taken the cube root of everything that I can take the cube root of, and now whatever I could not take the cube root of stays in the radical. So there would be my answer for number 10. Hopefully this is making sense to you guys. If you have any questions, just let me know. 2 more examples. Number 11, cube root of a over negative 27. Use your quotient property to break them up into their own radicals. Cube root of a over the cube root of negative 27, and then simplify each radical. I can't simplify cube root of a, so it'll just stay like it is. It's already in simplest form. Cube root of negative 27 would give me negative 3. This fraction is already in simplest form, so here's my answer for number 11. And then number 12. Once again, using my quotient property to give the numerator its own cube root. And my denominator its own cube root. So up top, I got to simplify my radical. So I want to try to find the biggest perfect cube that goes into 25. None of my perfect cubes go into 25, so I cannot break it down. C to the 7th, we need a multiple of 3, so it'll be c to the 6th times c. And then d to the 3rd is already a multiple of 3, so I can leave it like it is. And then the cube root of 64 gives me 4. Now I'm not done yet. I'm still simplifying the numerator. 25 we cannot take the cube root of. I know you can take the square root of it, but you cannot take the cube root of it. So that'll stay in the radical. Cube root of c to the 6th, I'm dividing my exponent by my index to get c's new exponent. 6 divided by 3 gives me 2, so I get c squared outside the radical. I cannot take the square root of c, so that'll stay. And then the cube root of d to the 3rd would just give me d, doing my exponent divided by my index. So that leaves 25c under my cube root. And then I still have 4 in my denominator. This fraction cannot be simplified any further. So here's my answer for number 12. So that's us simplifying our cube roots. It'd be the same concept for finding the 4th root of something. Let me erase these perfect cubes. So say I wanted you to find the 4th root of something, you would find the biggest or perfect 4th root that goes into our radicand. So you'd want perfect 4th roots. 2 to the 4th gives me 16. So 16 is a perfect 4th root. 3 to the 4th would give me 81. So 81 would be a perfect 4th root. So if I asked you to find the 4th root of 32, 16 is my biggest 4th root. My biggest 4th root that goes into 32. So I'd break it up like that. Take the 4th root of 16, which would give me 2. 4th root of 2. That'd be me simplifying a bigger root. Same thing for 5th roots, 6th roots. You're just finding the biggest, perfect, whatever root you're finding that goes into your radicand. Today we're just going to look at cube roots though. That's what your homework's going to be over. So your homework is page 297, numbers 29 through 36 all. Look on Canvas for the due date, and y'all have a great day.